Phonetics now is a very well-studied field, and there's a lot of excellent resources available online, for example. For example, you can find vowel charts and consonant charts for any particular language you might want to learn about, or your own language. And so this information is readily available. And I thought I'd talk about something which is a little less well known. So what I want to talk about is where the human speech organs came from. And an intriguing fact about the human speech organs is they're virtually the same as the organs in our mammal cousins. For example, if you take a sagittal section of the chimpanzee, a sagittal section means you cut the body this way and look at it from the side, you'll see that the chimpanzee has essentially the same speech organs as the human. That would be teeth, lips, tongue, there's hard palate, soft palate, uvula, there's the nasal passages, there's the epiglottis and the vocal cords, and so on. So if the human speech organs are virtually identical to the chimpanzee speech organs, although I shouldn't say speech organs, because the chimpanzee doesn't really use them for speech, at least not in the same way. And then even a cat has similar structure to humans. So then the question is, how did these speech organs arise? And from the comparisons I was just talking about, we can deduce that they didn't arise in order to enable speech. They must have arisen for another purpose and then been adapted for speech. So what is that other purpose? Well, I think the most interesting organizational principle comes from the fact that our ingestive and digestive system and our respiratory system, the system, so that's first the system for eating food and drinking, and the respiratory system is the system for breathing, they are overlaid upon each other. So that means from the lips here and down to the voice box, the glottis, these systems overlap. What does that mean? Well, it means that there's a certain risk involved when we eat, because if food gets into the lungs or water gets into the lungs, that can be deadly, have deadly consequences. So it seems that what has happened over the course of evolution is certain structures developed to separate the functions of ingestion and respiration. And then I'll make the claim that those structures then were adapted for speech. So how does this work? So in animals such as fish who don't have lungs, it's not a problem. But with the emergence of land animals, reptiles and so on, amphibians, reptiles, mammals, those animals developed lungs over the course of time. And then it became an issue that your breathing and your eating may interfere with each other with deadly consequences. So the primary structure to separate these two functions is actually the vocal cords. Okay, the vocal cords are soft tissue. There's two halves, and they're housed in the larynx, which is this cartilaginous structure right here. It's also called the voice box or the Adam's apple. And one thing about when you swallow, your larynx raises up, or your voice box or your Adam's apple. Why does that happen? Well, there's another cartilaginous structure called the epiglottis, which is a little flap at the entrance of the lungs. So when you swallow and the voice box goes up, the epiglottis comes down, and that is to keep food and liquid out of your lungs. But that's not a very good seal. So the real seal is the vocal cords, because housed in this cartilaginous structure, they can close and create a tight seal. Okay, so the primary function apparently of the vocal cords is not to produce sound, but it's to keep, to create a barrier for the lungs. But because of the way it's structured, then when we force air through, due to pressure differentials, very complex vibrations are set up, and that enables us to produce voicing, which is a major component of speech. Now, so that's probably the most important structure in speech is the vocal cords. Now, obviously, lips, tongue, and teeth were primarily for chewing and swallowing, so there's not too much to say about them. But the second structure I want to talk about is the hard palate. So if you look inside the mouth of a frog, there's just the mouth and there's two nostrils. So when a frog takes in food, the food is not compartmentalized into just part of the mouth, it's just in the mouth. So it's important then to compartmentalize the food we take in and to keep it, let's say, out of our nose. So what we have is an emergence of a secondary palate. So in our mouths there's the hard palate, and above the hard palate there are the nasal passages. And above the roof of the nasal passages is called the reptilian palate. So what we see in the evolution of certain dinosaurs is a secondary palate emerge, and in utero, human babies also, we can see that the secondary palate emerges after a certain number of weeks, and the two sides then come together to join it. So because then we have the oral tract, and then we have the nasal tract, we can differentiate the function of eating and breathing somewhat better. But because of those structures, then we can distinguish in human speech between oral sounds and nasal sounds. So the soft palate, or the velum, which is behind the hard palate, can either close the nasal passages and allow air to just flow through the mouth, or it can open the nasal passages and then air can flow through the nose as well as the mouth. So this enables us then to make two kinds of general sounds. We can make just an oral sound like ah, or I can open up my nasal passages and make it nasal as well, and I can say ah. So we see then that the ability to make oral versus nasal distinctions then arose from the development of the secondary palate on top of the hard palate. So then we see that in various ways we can understand how the speech organs arose, and it's kind of an important fact that they didn't arise to enable us to make speech sounds, but they presumably arose just for the reason I stated, to keep breathing and eating or ingesting separate. So what's the difference between us and the other mammals such as cats and chimpanzees that enabled language to emerge? It has to be rewiring of the brain itself rather than some physical change. So that's what I wanted to say about articulatory phonetics. And I could briefly say then, how does this explain acoustic phonetics? And the simple explanation is that the air being forced through the closed vocal cords is a very complex creates a very complex kind of sound with many with a single fundamental frequency and many smaller frequencies. And when we produce vowels, what we do is change the shape of our mouth to select some portion of those sound waves from the complex sound waves and turn them into resonant frequencies, and other frequencies are muted, and that's how we can distinguish vowels like ah, e, u, e, and o. So I was talking about voicing, which is when the air is more or less forced through this tight seal in the vocal cords, and how that produces a complex sound wave. Now, voiced sounds are found among consonants, but they really come on their own for vowels. So the question then is, how are vowels distinguished from each other? So there's a comparison we can make with a musical instrument such as a trumpet or a trombone. And let me talk about a trombone. So for trombone players out there, I'm going to simplify things a little bit. But basically, at the mouthpiece, you create a buzzing sound. And the buzzing sound is actually not very acoustically pleasing, because all of those subcomponents of the vibration are mixed together, and you get this buzzing sound. But ironically, we say about that sound that it's rich in harmonics. It doesn't sound like you might expect to hear that it's rich in harmonics, because it's just this kind of uninteresting buzzing sound. But what happens is that those sound waves then travel through the tube of the trombone, and based on the length of the trombone, some of those sound waves are selected and turned into resonant frequencies, and others are muted. And so as you change the length of the trombone tube by moving your arm in and out, a different of those component frequencies are selected, and you hear different notes. So let's think about humans. What corresponds to the mouthpiece in the trombone is the vocal cords in the human. So what do we do instead? Well, we produce different shapes by raising and lowering our jaw, raising and lowering our tongue, and moving our tongue forward and backward. And we can also make our mouths more tense or more relaxed. And we can spread our lips or round our lips. And all those are, physical actions are ways of selecting out of those complex sound waves that we that emanate from our closed vocal cords. So the most basic sound wave then would be the neutral vowel, which is something like in English maybe or In the neutral vowel, there's very little tension in the mouth, and it's mostly a regular tube from the vocal cords all the way to the lips. So it's a kind of it's a tube that's closed at one end and open at the end of the lips. So that's going to produce resonant frequencies for all the sound waves that would have a node at the closed end and an antinode at the open end. And so that'll give us this very regular pattern when we look at the spectrogram for this sound wave. The spectrogram is a kind of visual interpretation of it. And what we'll see is these thick bands of resonance, which are called formants, and we'll see that they're evenly spaced from bottom to top. Moreover, they have an interesting mathematical relationship whereby the second formant is 3 times the first formant, and the third formant is 5 times the first formant, and so on. They go up by all odd multiples. And if I had more time, and if I had a blackboard, I'd tell you how that mathematical relationship enables us to verify the analysis that I just proposed.